Hello everyone, I'm Wildberger. Today we're going to carry on talking about determinants, and I want to connect this important object with permutations. So kind of a connection between linear algebra and what we call group theory in mathematics. So I'm not going to be able to cover all of this exactly logically coherently because there's some critical facts that I can tell you what they are, but proving them requires a kind of an excursion into algebra, and I don't have time to do that. But I still want you to see a certain alternate formula for a determinant. So let me remind you that if A is an n by n matrix, then the determinant of A, which also we sometimes write just without brackets, and sometimes we write it with sort of an absolute values around A. This is a number. Okay. It's a number associated to the matrix, defined recursively or inductively as follows. First of all, we define the determinant of a 1 by 1 matrix A just to be equal to A. And then we say that if in general A is equal to, say, entries little a I j, and if we also denote by capital A I j the n minus 1 by n minus 1 submatrix obtained by removing the ith row and the jth column, then here is our formula for the determinant of A. Determinant of A equals A11 times the determinant of A sub 1, 1, then minus A12 times the determinant of A12, and then plus, and then minus, and so on, all the way up to minus 1 to the, there's n of them altogether, n plus 1. Last time I wrote n, should have written n plus 1. N plus 1 times A1n times the determinant of capital A1n. So that's our inductive formula, okay? So let me illustrate this again just to make sure we're all on the same page. I'm going to do it with a 3 by 3 matrix, but now with the entries a little bit more organized, not A, B's, and C's, but rather A, I, J's. So let's suppose that A is a 3 by 3 matrix, A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, so then how do we calculate the determinant from this formula? So the determinant of A equals, so first of all, A11 times the 2 by 2 determinant, and I'm going to write that with square brackets, of this sort of submatrix. In this case, the submatrix is right here. Okay, the entries are A22, A23, A32, A33, and then minus A12 times the submatrix obtained by eliminating the row and column through A12, and that's the matrix A21, A23, A31, and A33. And then finally plus A13 times the 2 by 2 matrix A21, A22, A31, and A32. Okay. Now each of these 2 by 2 determinants we can calculate. So this first one will be A22 times A33 minus A maybe 23 times A32, okay, and then minus A12 times A21, A33 minus A31, A23, and then finally plus A13 times A21, A32 minus A31, What does that say? 2, 2, I guess. Okay, let's expand this out. We know that we can get 6 terms. A11, A22, A33, minus A11, A23, A32, then plus A12, I might write the positive one, A31, A23, minus A12, A21, A33, plus A13, A21, A32, and minus A13, A31, A22. Great. So that is the determinant of this general 3x3 matrix. And I've written it in this way because I want to now connect this with permutation. So there's another way of thinking about this quantity, and it relates to really rooks on a chessboard. So let me remind you that if you have a chessboard, okay, maybe a 4x4 chessboard, there it is there, and there's typically black and white squares, black, something like this. Fine, and I remind you that a rook, let's say a rook, something like this, okay, a rook is a chess piece which can take either in the horizontal or in the vertical direction. So a rook, that's supposed to be a rook. A rook is a chess piece that can take horizontally or vertically. And what's kind of interesting is a placement of rooks on a chessboard so that none of them are able to take each other. Okay, so let's consider positionings of n rooks on an n by n chessboard so that none can take any other. So example here, if I wanted to complete this story here, maybe I could put another rook over here. Okay, those two rooks are not taking each other. And then maybe I could put another rook down here in the corner. That one's not taking any of the two previous ones. And then I could put the fourth rook over here. Okay, so those 4 rooks are happily situated. They're all kind of peacefully oriented. None is able to take each other. Now, how many such positionings are there? There are n factorial such rook positionings. Why is that? Well, if we say go from row to row, going from one row to another, there's n choices for the first row. In other words, if we look just concentrating on this first row, there'll be n possible places for the rook in that row. And then in the second row, then n minus 1 choices in the second row, because we're not allowed to put the rook in the same column that's already been occupied by the rook in the first row. And then, well, and then n minus 2, etc., down to 1 in the last row. Right. So in the 4x4, you have 4 choices in the first row, 3 choices in the second row, then you'll only have 2 choices in the third row, and then finally in the fourth row, only 1 choice. So there'll be altogether 4 times 3 times 2 times 1, that's 24, or 4 factorial different ways of positioning the rooks. Now, these 24, or in general, n factorial rook positions are intimately connected with determinants. And have a look at what we obtained in the 3x3 case. Okay, so if we go back to this formula here, and maybe I will see if I can maybe draw some chessboards here. So maybe here's a little chessboard. It'll only be a small one because it'll only be 3x3. Okay, there's a 3x3. Okay. This first term right here, okay, this first term corresponds to 3 positions. Remember how we're sort of organizing the matrix entries, okay? This is the 1-1 entry. This is the 2-2 entry. This is the 3-3 entry. So this first term that I've underlined corresponds to a rook positioning where the 3 rooks are along the diagonal. How about the second one, maybe in green, the second one here, okay? A11, so that's, I'll put it there, A11, A23, that's over there, and A32, okay? That's another possible positioning of the 3 rooks on this 3x3 chessboard. And then maybe this next one, maybe yellow, okay? A12, so that will be that one there, and then A31, that's I guess down here, and then A23, that's over here. That's another positioning, okay? And the other 3 correspond to other ones. Let me just actually complete that. A1, 2, 2, 1, 3, 3. The A1, 2, that's that one there, and then A2, 1, and then A3, 3. That's that one there. And how about this one here? A13, 1-3, then 2-1, and then 3-2. Here's another one. And finally, maybe in blue, this one here, A13, that's that one there, A3-1, that's that one there, and A2-2. Okay, so those are the 6 possible positionings, and they exactly correspond to the terms of this determinant once we've expanded it all out in terms of the entries. But there's one more piece of information, which is actually the most subtle aspect of this entire story, which is that these 6 terms come with plus and minus signs. The coefficients are always either +1 or -1, and half of them are +1 and the other half are -1. So to completely describe this situation, we really have to sort of say what the sign is, okay? So let me tell you what the general sort of theorem is and what's actually involved to describe this story. So there's a theorem which connects the theory of determinants with group theory. And it is that if A is an n by n matrix, say with entries little a, I, j, okay, is an n by n matrix, then here is an alternate formula for the determinant of A. The determinant of A is the sum, okay, over pi, I'm going to write, I'll explain it in a second, permutations of n. Okay, permutations of n. And then something which we'll call sine of pi. That's going to be either plus or minus 1. That's the critical sign of each of the terms. And then the terms all look like this. So there'll be an A1 pi 1. And then A2 pi 2. All the way up to AN pi n. Okay, where sine of pi, which is either plus or minus 1, is the sign of the permutation pi. What is the permutation pi? It's a map, if you like, from the set 1 to n to 1 to n, which is a bijection. That it's a 1-to-1 mapping. You've got n boys, you've got n girls. You're matching up the boys with the girls in exactly a 1-to-1 way. So each boy gets a girl and vice versa. Now, I have to complete the story, I have to tell you what the sign is. So here, the sign of pi is -1 to the, say, k, where k transpositions. Get you from pi to the identity. Okay, I have to explain this. Even though to explain completely would take me far afield, but I want to at least give you an idea. So let's say we are in the 3 by 3 case. Okay, so example. So suppose that we have n equals 3, and here is a permutation. So how could I describe a permutation? I could describe it by what it does to the 3 elements. It's mapping the 3 elements to the other 3 elements. Now suppose that 1 gets sent to 2, and 2 gets sent to 3, and 3 gets sent to 1. So you got 1, 2, 3, and maybe these things we're mapping things, and so at the end of that, the thing in the first spot goes in the second spot, the thing in the second spot goes in the third spot, like this, and the thing in the third spot goes in the first spot. Maybe that's one way of describing it. Okay, now suppose that we wanted to get back to the original position, but we are only allowed to make swaps between pairs of objects. Okay, so that's what a transposition is. It's a swap between a pair of objects. How many swaps do we need to get back to where we started? But we're only allowed to sort of move 2 of them at a time by interchanging any 2. Okay, so let's try. Let's interchange the 1 and the 3. Okay, that's a swap or a transposition. It's interchanged the 1 and the 3. But it's still not in the correct order. To finish it, I would need to swap these guys. If I did that, okay, I'm going to now get them back in the right order. So I made 2 swaps. What does that tell me? It tells me that the sign of this particular permutation, pi, is -1 to the 2. 2 because there's 2 swaps. Okay, and that is +1. Now, if we go back up here to our 3 by 3, so I remind you the permutation is like 2, 3, 1. So which of these 6 terms is 2, 3, 1? Where 1 is associated to 2, 2 is associated to 3, and 3 is associated to 1. It's exactly this one here. Okay, so see, this term corresponds to the permutation that 1 gets sent to 2, 2 gets sent to 3, and 3 gets sent to 1. So this permutation that I just circled corresponds to this permutation, and we could also describe it in terms of our chessboard. That happens to be the 1, 2 entry, so that's that one there, and the 2, 3 entry, that's that one there, and the 3, 1 entry, that's that one there. Now, how many swaps do you need to get this thing back in the identity? Well, so you could do it with rooks if you like. Got 3 rooks like this, and you can swap. Let's say swap the rows or the columns of any rooks. Suppose we decide to swap the rows, these rows here. Okay, so we're going to swap them, and there we swap the rows. And now we're going to swap these rows. Okay, look at that. This is the kind of geometrical interpretation of what I was doing up there. So what we have then is this idea that every permutation has associated to it a number which is either plus or minus 1, and that number is minus 1 to the number of swaps that you need to sort of get back to the identity from whatever permutation you've considered. Now, there is a difficulty here, or it's a theoretical extra piece of information that you need to know that I haven't proved to you. That's a little bit challenging to prove. So an extra requirement to this entire story. We need to prove that the sign of a permutation is well defined. What does that mean? Well, it means that, let's say we've done a permutation, and then I come along and I start swapping two at a time, back and forth, and it takes me 27 swaps. Let's see, it's a big thing. 27 swaps to get back to the identity. So then I would calculate that the sign of this big permutation is minus 1, because it's minus 1 to the 27. But now you could come along to the same permutation and get back to the identity maybe in a more efficient way. Maybe it will take you only 11 swaps. Okay, you can somehow get back to where you started with 11 swaps because you're more clever. Then you would also calculate that the sign is minus 1 to the 11, which is also minus 1. So we were in agreement. So the theoretical requirement here is to prove that the sign of pi is actually well defined. And unfortunately, in most every linear algebra course, okay, the algebraic sophistication is not there to prove this, and probably we don't have enough time or inclination to prove it either. But you should know that this is a key kind of algebraic aspect which underlies the theory of determinants, which is maybe often put under the carpet, but it's actually a critical issue, is the issue of these signs and how they behave, and first of all that they're well defined. Okay, so having said all that, that's great, but still let's come back to our theorem. Still, this then is a very nice sort of fact that you can appreciate, and I think you can perhaps see why, at least at some level, this is reasonable. Because when we were doing this original determinant definition, okay, like in this 3x3 case, what we were doing is we were starting with A11, that's our first term right there, A11, and then we were multiplying it by the determinant of this 2x2 block opposite it. Now, if you know that this determinant of this 2x2 block consists of a lot of terms, each of one which consists of a product of elements, one in each row and column, like maybe this one times this one, okay, or maybe this one times this one. Then when we take those sums of terms and we multiply by A11, we're going to get exactly the same kind of thing. In other words, we're going from a 2x2 rook configuration, or rook configurations, to a bunch of 3x3 rook configurations by taking the 2x2 rook configurations and adding a third rook, which is in position 1, 1. That corresponds to that first term. And when we do the second term, well, it's like we're doing the same kind of thing, but now we're starting with this thing here, putting a rook there, and then looking at these other four things, which is a little bit harder to draw, okay, because it's a kind of a block thing. It's these four things there. And considering rook positions there to get a total rook position for the entire 3x3. So this formula that I've defined the determinant originally for is pretty closely connected with this permutation formula here, except that the role of the sign is not so clear. It needs to be more carefully analyzed to pin it all down. But I think you can at least see that it's kind of reasonable. Okay, what are some consequences of this in terms of calculating determinants or something like that? Well, let's say we have a diagonal matrix. Okay, so suppose A is the diagonal matrix, 4, 3, 1, 7, and otherwise it's all zeros. It happens to be a 4 by 4. What is its determinant going to be? Well, then determinant of A, if you remember this previous formula, the one I've just shown you, the one with the sum over all permutations, this determinant is a bunch of terms with coefficients plus or minus 1, each corresponding to a position of Rooks on the 4x4 board that don't touch each other. And those products are going to be non-zero precisely when the Rooks are all on positions where there are numbers which are not zero. In other words, if we take this particular, say, Rook configuration, that one, that one, and what else? And maybe that and that one there, okay? That's a Rook configuration. But it has a 0 in it. It has actually 2 zeros in it. So if we take the product of those 4 entries, we get 0 times 3 times 0 times 7. That's obviously 0. It's not going to contribute anything to this sum, this signed sum involved in the determinant. All right. So that Rook position doesn't contribute. And in this case, there's only one Rook position that contributes, right? There's only one way of placing the Rooks on the 4x4 board so that every Rook is covering something that's non-zero. And here it is right here. We have to choose that position in that row, that position in that row, that position in that row, and that position in that row. Right. And that corresponds to the permutation. 1 goes to 1, 2 goes to 2, 3 goes to 3, and 4 goes to 4. So the sign of that permutation is +1, because there's no swaps needed to get it back to the identity. It is already the identity. And so the determinant of A in this case will just be that big sum just reduces to a single sum, A11 times A22 times A33 times A44. All the other 23 terms, because there's 4 factorial terms altogether in this 4x4 in general, will be 0. And in this case, we're just getting the product of the diagonal elements. It's 4 times 3 times 1 times 7.